So this is absolute and conditional convergence for sequences and series. And for the series of the sum of u sub n is called absolutely convergent if the sum of the absolute value of u sub n, which is just a sequence, if the absolute value of u sub n converges when you take the sum of it. The series of the sum of u sub n is called conditionally convergent if it converges, but when you take the absolute value of it and sum the terms up, it diverges. And examples are the sum of -1 to the power of n minus 1 times n, because it goes 1, then -2, +3, -4, +5, -6, and so on. So it goes back and forth like that. And then when you take the absolute value of it, the negatives turn positive, so it just goes to 1, +2, +3, +4, +5, +6, and diverges. Let's see if I can open up more. Okay, and now here's the comparison test. If u sub n and v sub n are both series, and if u sub n and v sub n are both greater than or equal to 0, and v sub n converges, then if u sub n is greater than 0 but less than v sub n, then u sub n converges also. An example of this is, since 1 over 2 to the n plus 1 is less than 1 over 2 to the n, and we know that the sum of 1 over 2 to the n converges, then that means that 1 over 2 to the n plus 1 converges also. And for divergence, if u sub n and v sub n are both series, and if u sub n and v sub n are both greater than or equal to 0, and v sub n diverges, then if u sub n is greater than or equal to v sub n, then u sub n diverges also. An example of this is, since 1 over the natural log of n is greater than 1 over n, and we know that 1 over n diverges, since it's the harmonic series, then we know that 1 over the natural log of n diverges also. And we'll go to the next one, geometric P series. Alright, geometric series. The sum of a times r to the n minus 1 power equals a plus a times r plus a times r squared plus a times r cubed plus ... where a and r are constants, which is the definition of a geometric series. And also it converges to s equals a over 1 minus r if the absolute value of r is less than 1, and diverges if the absolute value of r is greater than or equal to 1. And the sum of the first n terms is s sub n equals a times the quantity of 1 minus r to the n power all over 1 minus r. And P series, which is a special form of sequences and series, is the sum of 1 over n to the p power, which equals 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on, where p is a constant, and converges for p is greater than 1 and diverges for p is less than or equal to 1. The series for p equals 1 is called the harmonic series, which is the sum of 1 over n equals 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. The integral test is for a series S sub n, it will only converge if and only if the integral of that function dn converges from 1 to positive infinity. Examples are the series 1 over n squared, which the integral from 1 to positive infinity is 1 of 1 over n squared dn equals the limit as I chose x to be the variable that approaches infinity. 1 over n squared dn equals the limit as x approaches positive infinity of negative 1 over n, which the derivative of negative 1 over n is just 1 over n squared. So then n from 1 to x equals negative 1 over x minus negative 1 equals negative 1 over x plus 1 equals negative 1 over infinity plus 1, and negative 1 over infinity just approaches 0. So 0 plus 1 equals 1, and since that converges, then 1 over n squared also converges. The alternating series test. An alternating series is the sum of negative 1 to the n plus 1 power times a sub n, some series, equals a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus a sub 5, and so on. An alternating series converges if these two following conditions are satisfied. First, u sub n plus 1, the absolute value of that must be less than or equal to the absolute value of u sub n. And the limit as n approaches positive infinity of u sub n equals 0 for the sequence or the sequence of series u sub n. And you can pause this if you ever need to look at it more. Tonic sequences. Okay. Oh wait, what's going on? Okay. Alright, so the ratio test. If you let the limit as n approaches positive infinity of u sub n plus 1 over u sub n equal L, then the series of the sum of u sub n converges absolutely if L is less than 1 and diverges if L is greater than 1. If L equals 1, the test fails and you can get no conclusion out of it. Example is u sub n equals 2 to the n power, and so the limit as n approaches positive infinity of 2 to the n plus 1 over 2 to the n equals, and let's just say, for example, if n equals 2, the limit as n approaches 2 of 2 to the 2 plus 1 over 2 to the 2 equals 8 over 4, because 2 to the third power is 8 and 2 squared is 4, and 8 over 4 equals 2, and since 2 is greater than 1, this diverges. And just to use another term for n, just to test if it works also, if n equals 5, the limit as n approaches 5 of 2 to the 5 plus 1 power over 2 to the 5, absolute value of that equals the absolute value of 2 to the 6th over 2 to the 5 equals 64 over 32, which also equals 2, and again 2 is greater than 1, which diverges. Now, that was the ratio test. This is the root test. Let the limit as n approaches positive infinity of the n root of the absolute value of u sub n. That equals L. Then the series u sub n converges absolutely if L is less than 1 and diverges if L is greater than 1. If L equals 1, the test fails again. So let's just say u sub n equals n cubed. The limit as n approaches positive infinity of the nth root of the absolute value of n cubed. And let's just say if n equals 4, the fourth root of 4 cubed is the fourth root of 64, which is 2 times the fourth root of 4, which is approximately 2.828, which is still greater than 1, so therefore it diverges. And let's just say u sub n equals 1 over n, and we'll say n equals 2, then the limit of n approaches 2 of the square root of 1/2, which is approximately 0.707, which is less than 1, and therefore the sum of 1 over n converges. And now let's open up file. Oh my. Oh, alright, well, that's the end of this video.